Hello, everyone. Happy to see all of you early in the morning on a Saturday. Thanks for coming. I'm actually in Tashkent for the first time and in Uzbekistan too. Very nice place you've got here, and happy to see all of you. Who is from Uzbekistan, just out of curiosity? More than half, for sure. Very cool. All right. Hi, everyone again. My name's Vincent. I currently work at Yandex Go. I'm one of the architects of all of the backend services that power some of our services, such as taxi, scooters, partially also delivery, food delivery, all of this kind of stuff. I've been in the industry for about 14 years. I'm actually older than most of you probably think based on what I look like. And during this time, I've worked at a variety of different companies, including Spotify. Some of you might know. Who uses Spotify? Give me a show of hands. Okay, a few people. Google, obviously everybody knows Google. DeepMind, which is Google's department that deals with artificial intelligence. And of course now Yandex. Along the way, I've done a couple of different things for smaller companies too. There's a few examples about this that I'll tell you later in the talk. But I think we can get to that when the time comes. In addition to my professional work, I think one important thing I'd like to point out is that I've done a lot of open source work. So there's various open source projects that I've either started, contributed to, and so on. And I think that also kind of shapes and influences the way I look at tech in general. My experience technically is kind of diverse. So I started out being one of those people who really loves functional programming. Any functional programming enthusiasts, Haskell, Erlang, that kind of stuff? No hands, okay. But I've kind of moved away from that over the years and turned to a way of thinking where the main thing that's important for me is that things should be as simple as possible, which is something I'm going to talk about a lot. All right, my talk is going to be a bit of a mishmash of things about the life cycle of large systems and how they usually evolve from a napkin where you scribble down some ideas to ultimately becoming some kind of legacy system. And I hope I've sort of managed to weave this into a coherent sort of story for you. The main thing I hope for all of you to take away from this at the end is some ideas, some suggestions for how you can apply some of my experience in your own work and make sure that the things that you're going to build in your future career are going to be better. All right. The first thing that we kind of need to talk about to get a sort of shared understanding is what actually is a large system. The actual thing is that a large system is not a homogeneous kind of thing. It actually is not a straightforward question. There's many different kind of things that affect whether or not a system is large. We've heard a definition here which I liked in terms of the impact of a system. And of course, there's also definitions in terms of the technical size and complexity of a system. In reality, I think it's sort of a mix of several criteria, not all of which have to apply in order for a system to be considered large. I'm going to give you 4 of the criteria that I think are very important for determining whether or not something is actually a large system. Then we kind of get a shared understanding with you. We can move on to how they usually evolve. So the first thing that I'd like to point out is actually not a technical thing. In fact, most of the 4 criteria are not really technical. The first thing is, can a single person understand what is going on in that system? And there's an example which I like to use for this, which is I run a service at home, literally on a small server in my flat in Moscow, which gives me something like a music streaming service, sort of similar to Spotify. That is a software program, open source project called Gonik, and it's mostly written by a single guy. That project does a lot of actually fairly complicated stuff. There's like live transcoding of music into different formats based on the available network bandwidth and so on. But still, all of the features of this single project, this one guy can kind of keep in his head and understand what's going on and how it all fits together. If we look at some other project as an example, for example, the Linux kernel, which I think most of you are probably familiar with, that is a much larger project, which, albeit being started by a single guy, Linus Torvalds, is no longer something that Linus himself can fully understand. So there's hundreds of subsystems. They all have their own individual complexity. They all have their own individual maintainers. And at that point, Linus is more like a figure at the top who's kind of pulling in changes from several different subsystems, but he doesn't understand every single bit that's going on in Linux, all of the different hardware support aspects and so on. So Linux kind of is a system that doesn't fit in one person, if you will, whereas Gonik still is. The second thing that I think is also important, it's also non-technical, is have multiple generations of people worked on a thing. This is sort of a proxy metric for several other things, such as the age of a system. Obviously, if there's been several generations of developers dealing with the thing, it's probably more than a few months old. And it's also a sort of proxy metric for the importance of a system. That is, if a system is not important, there's probably no point in like keeping it maintained, changing the developers that are working on it, and so on. So in a large system, I think what you often see is the sort of metaphorical handover from an older generation of engineers working on the system to a newer generation. Of course, it doesn't really happen like in this example picture. It's more of a continuous process where people who might have been working on one project move on to other projects, new people join, leave, and so on. A great example of this is the backend of Yandex Ads, so our advertisement system. In Yandex Ads, initially, the system that runs the backend was written by a small number of people, and they mostly understood what was going on in that system. It's actually lovingly called Dvizhok, the engine, because that really is the best way to describe what is going on in that thing. At this point, this is now like almost 20 years, I think, after the start of the development of that project, there's dozens, maybe even hundreds of people working on Dvizhok, and nobody really knows everything that's going on in that system anymore. So it's actually the two things that I talked about here combined. There's now new people working on the system. The original developers have either left or moved on to other roles, and no single person can understand what is going on in that thing anymore. All right, the first technical kind of item is what I call operational complexity. So at some of the companies that I worked at, specifically at Google and my first role at Yandex, I was a site reliability engineer. Site reliability engineering is sort of the art, if you will, of writing software that runs your software better. So if let's say you make a web service, your web service initially has 100 users or so, and you scale up to 10,000 users. Let's imagine this very first part. You have 100 users, and you have maybe 2 people responsible for keeping your system running. If something breaks, they get a phone call, they deal with it, and they kind of fix it. Now imagine it scales to 10,000 users. Do you now need 200 people maintaining the system or not? If you do, then there's something wrong. And the point of SRE is exactly to automate away all of the manual bits and kind of deal with the operational complexity that way. As it comes to large systems, I think any kind of system where you need to do this kind of thing, for example, write code just to be able to run your code, is already a good indication of that system being large enough to be, well, considered a large system. 2 other aspects related to operational complexity are how important is the system if it goes down. It's kind of similar to what you said about impact earlier on. If the system goes down and it affects a large number of people, then that also raises its importance. And I think in my mind, it also raises the operational complexity involved and thus pushes it closer to being a large system. An interesting example here is also something like the firmware for an Internet of Things device. Imagine you have a smartwatch or something. The firmware of the smartwatch itself might be fairly simple. This actually isn't a smartwatch, by the way, but still. But if you are making changes to the firmware of such a device, you want to be really careful about rolling it out. You might break somebody's smartwatch. After that, they can't install updates anymore and so on. You have to put really a lot of time into the operational aspect of that sort of thing. So I consider these sorts of things, not just the firmware itself, but all of the surrounding aspects, a large system. And the final thing is the plain sort of technical definition, if you will. It's what you said about millions of users and so on. Imagine you write something like a link shortening service, a simple website where people paste the URL and they get like a shortened version of that. If you have 100 users or even 1,000 users, you can run like a small binary on a home server written in Go or whatever, it doesn't matter, and it's going to be fine. If you scale this thing up to 1 billion users and like millions of RPS, simply due to physical constraints, you're going to suddenly need a lot more sort of engineering investment into the system to actually keep it running. Does that make sense to you so far? Nobody's saying no. I think that's a good sign. Okay. Let's talk about the topology of these systems. So topology is kind of an important thing here because, as I've pointed out, for example, in the Internet of Things firmware case, there might be more than just the individual software project. I think what some of you are thinking about when I say large system is literally like some piece of software, maybe a backend server and a front-end server written kind of as one unit. But things can very quickly escalate and get a lot larger than that. And large systems can also be composed of smaller parts that are not individually large. This kind of interesting slide is a real example of a part of the Yandex Taxi backend architecture. So these little blue boxes that we have, each one of these is actually an individual microservice. And the individual microservices, it doesn't really matter which ones these are not particularly complicated. There might be a service that does something like return information about a car, for example, the color of the car. But that service individually is not really complicated enough to be considered a large system. But if we consider all of these little lines between the services, which is the logical interactions, it's API calls, it's all of this sort of stuff, the system as a whole, consisting of all of these microservices, is definitely considered a large thing. In my team at Yandex, together with the reliability team, we work on kind of classifying which parts of these systems are important, not important, what exactly these logical connections should do. And we also work on making sure that it actually keeps running most of the time. Because, for example, Taxi not working has impacts on the real world pretty quickly. A couple of weeks ago, one of my colleagues, Sasha Fischer, actually gave a talk about this at another Yandex event here in Uzbekistan. He focused specifically on how we keep these systems running and reliable. If that's an interesting thing to you, actually maybe some of you have seen this talk, you can go and check it out. All right, I hope that we kind of have a bit of a shared understanding of what a large system is now. So there's social aspects, how many people have been working on the system, how complicated is the system, can a single person keep it in their head, how difficult is it to operate, how interconnected and large is it, and so on. And if we consider these criteria, we can kind of guess approximately at what a large system is. It kind of depends, of course, from case to case. And all of these systems sort of share the same kind of life cycle. I'm going to show you a simplified version of this life cycle. Of course, in real life, if you're working at a large company, for example, things are not really linear. But I think the overarching structure of what I'm going to explain to you holds true in most of these cases. Some of what I say might come across as a little bit cynical in some parts, but I think this is a good way for you to see sort of an exaggerated way of how things can go. And then you can kind of understand the extreme cases and try to optimize away from them in your own work. So this is what people usually aim for. This is what people kind of expect the life cycle of a large system to be. There's an initial part of the system where we deal with the design of the system. That is, we decide what to build, we decide how to build it. We kind of make a plan for how we can implement all of that stuff and get ready to start implementing. We then move on to the implementation itself, which is where we actually write the code, we test it, we maybe get some beta testers or alpha testers, real users that are going to try and use it. And once we're comfortable that the thing that we've built actually works and kind of matches what we designed, we put it in production. So this, for something like a web service, might be we actually make the web service available. If you're writing firmware for some device, this is the point where you ship the devices to users. If you're doing something like writing the firmware for a rocket at Roscosmos or something, this is the part where you launch the rocket into space, right? So it's when the code that you've written ends up actually being used. And ultimately, I've put a little dotted line here. You might get to a point where the system ends up being deprecated. Deprecation is kind of a natural part of systems. So anything you build right now, who knows, maybe it's around in 10 years, maybe it's not. Companies die, new companies form, replace old ones. Inside of companies, systems also get replaced, and so on. I consider this just kind of a natural part of what happens. All right, so this is kind of an idealized view. What actually happens in real life is closer to this. So instead of trying to design a system in like a reasonable way, we end up over-engineering, which means that we're doing stuff that isn't really related to our core business problems. We're picking technology that is much too complicated for what we're actually trying to achieve. And we end up with a design that doesn't really match what we should have had in an ideal world. We then move on to under-delivering. Under-delivering is when we take our kind of over-engineered sort of design, which already isn't really what we should be building, and we implement it badly. So things kind of diverge from our plan. We don't really get all of the stuff that we had planned for to work, and there's just a sort of general aura of problems all around us. And then instead of a smooth launch into production, we get firefighting. Firefighting is when our system has actually met real users, but it doesn't really work, and we end up spending all of our time dealing with these kinds of problems. I'll talk about all of these in more detail. But instead of deprecation, we get to the final point where a system lives on sort of forever in a sort of zombie state, if you will, as a legacy system alongside some other thing. All right, let's go and look at these in more detail. So over-engineering, I picked this image, which is a so-called Rube Goldberg machine. The idea of a Rube Goldberg machine is that you have some sort of super complicated mechanism that's almost impossible to understand. Imagine something like with like a marble rolling down a pipe, and it like falls onto a slope or whatever, and then it knocks over a domino and these kind of complicated things. And in the end, it just turns on a light switch. I think over-engineering is a kind of thing that occurs in software projects that leads to exactly this sort of design. So instead of a minimal thing that just pushes the light switch, we get this kind of impossible to understand machine which does whatever inside, and then if we're lucky, it might actually push the light switch in the end. And over-engineering gets you into this kind of situation where you end up with a system that is much more complex than it should have been. It's impossible to make it reliable, and nobody understands what's going on anymore. There's sort of three aspects of this that I've picked out specifically that occur in over-engineering that I think are important to kind of keep in mind when you start designing systems. The first one, and this is a favorite of software developers, even the most experienced people do this all of the time. It's picking complicated technology right at the start. Maybe you read Hacker News, for example, and you've read about this cool new JavaScript framework on Hacker News. You start a new project, and the first thing you do is you pick this, you add this framework to your dependencies and start writing your code based on that thing. But you didn't at this point consider whether that actually is the right fit for the project that you're trying to build. The second thing is trying to build something that is needlessly generic. That means that, for example, you're trying to build a service for delivering flowers. I'm going to use that example a couple of times. But instead of focusing on the problems related to delivering flowers, you start building a generic delivery system for absolutely everything in the world, including like furniture or whatever, which has completely different constraints. And the third thing that occurs is domain misunderstanding. The domain is sort of, if you will, the business perspective or the real world problem that your system is trying to solve. And if you slightly misunderstand what actually is required for that domain to work, you won't be able to design a system that is really able to fit the criteria of those real world cases. If you get this wrong, you end up in a situation where you have something that is called accidental complexity. Keep this in mind for now. I'll give you a clear definition of what exactly that means slightly later on in the talk. All right, I hope that makes sense so far. Okay, let me give you an example. This is actually a personal example from Spotify. So Spotify was one of my first jobs. I worked there about 13 years ago. I was much less experienced than I am now. And I did basically all of these things wrong that I just showed in a project that I was trying to build. So at Spotify, I worked in the internal IT department. We did stuff like maintaining LDAP, the user directory for internal employees and so on, for employees to be able to log in, use various internal services and so on. And we were doing this with a completely impenetrable, like 4,000-line Python script, which a bunch of people had written over several years. It was very difficult to understand what was going on in that thing, and it was all inside of one file, and inside of that one file, people were using different code styles and so on, so you couldn't even like clearly just read the thing from top to bottom and figure out what it was doing. And I came up with this brilliant idea, or so I thought at the time, of making a single giant system that would reconcile all of this. It would like connect to the HR system, get their Excel exports, it would connect to our LDAP, create the users there, it would like sync this to all of our various other databases and just kind of be this like general engine that synchronizes everything with everything. And the technologies I picked, the design I made at the time was just impossible to implement. So I started doing this and it just didn't really go anywhere. And I spent some months on this and we really didn't end up with anything that was working in any way. And people kept using the Python script. The only thing I had was like a small CLI tool that did parts of what the Python script could do. So what ultimately ended up happening is that the Python script just kept living on. My over-engineered solution didn't go anywhere. And ultimately we rewrote some small parts of this Python thing, the ones that were sort of the most painful, into small Java services, and the rest stayed as it is. I don't know what they're doing now at Spotify. This was a long time ago. I'm pretty sure that the script has actually been removed at this point, but I think it still lived on for quite a few years after the time that I left. All right, the next thing we get to is under-delivering. Who's seen this meme before? Few people, yeah. So under-delivering kind of goes exactly like this. You start out at the beginning with like the most beautiful sort of implementation plan. You like bootstrap your project, everything is great, you've set up CI or whatever. And then as things move along, the quality of your project kind of gradually decreases. And also you run out of time. Business comes to you and says you have to ship next week. We have to like launch this to users now. And the final parts of the implementation kind of end up not exactly on the same level of quality as what was going on at the beginning. So again, there's kind of three main things of what's going on during these kinds of things. The first one is timeline drift. So you may have come up with a design, and during the design you said this will take us 3 months to implement, or 2 weeks to implement, or whatever. But then as you start doing it, you realize that there's a lot of small edge cases, problem stuff you didn't consider. The problem is actually more complicated than you thought. And you kind of keep pushing back the time. Projects get delayed. From 2 weeks, we move on to 6 months. People are already kind of giving up. And ultimately, like in the case of my project at Spotify, for example, the state just gets to it's complicated. And people might even get to a point where they realize this is never really going to launch. The second thing that happens is spiraling complexity. So you discover more problems that you need to solve, and you may not have planned for these problems. So you start trying to, for example, drag in additional dependencies. You found a library here on PyPy or whatever, which seems to fix the problem that you have. So you drop this library into your project, and things just end up becoming even more complicated because maybe that library dragged in some other really complicated thing, maybe an async I/O engine or whatever, and the complexity of your system just keeps growing and growing and growing, and it kind of spirals out of control. The third thing is connecting the wrong dots. You all know probably these things where you're supposed to draw an image by connecting dots that are numbered. So like you're drawing a horse or whatever, like in my previous slide, by connecting all the dots in the correct order. What happens in under-delivering is that it turns out that the dots that you drew during the design don't actually sum up to a horse, and you start kind of connecting them in a slightly different way. So you're no longer really following your design. You've diverged from the plan completely. Your thing is super complex and it's delayed. This is a classic kind of under-delivering case. So again, I have a personal example here, though I consider myself to not be the person that's at fault for this one at least, which was at a company in Norway that I worked at in 2015 or so. And that company made large machines. I can't name the company. They made large machines that they sold to various business customers. And these machines were connected to the internet, sending sorts of device data, sensors, current device status, and so on. They were mostly using this data for kind of internal maintenance. And at some point, somebody thought, wouldn't it be great if we could give our customers like an online dashboard where they see the device status and they can kind of just like go and click and see what's going on. So what they did is they hired a giant consulting company to do this. So this company itself, the Norwegian company, they're not an IT company. They do physical engineering. They're, if you will, real engineers, yeah, not software engineers. It's a common joke. But they don't really know anything about software. So they bring in this giant consultancy. Lots of people in suits tell them that it's going to be great. We're going to build the best thing ever. We've put 500 developers on the task. And then these 500 developers, I have no idea what they were doing for a year and a half, but they ended up writing a giant amount of Java, which didn't work at all. At the same time, they told them that we need to run this Java on Amazon, and you should sign contracts with Amazon and make sure that we can kind of use all of the Amazon services that we want. So what ended up happening is this thing just didn't work. And they brought me in, together with a couple of other freelancers at the time, to first figure out what was wrong with the system that had been implemented, and further on to actually try and build a new solution. So here's something strange happened. We built a prototype, an actual working prototype, literally in 1 weekend. So we had a thing that we could show to the business and be like, hey guys, this is like a working thing. This does exactly what you want. And we can work on this slightly more and turn this into something that is production ready. And they came back and said, yes, but we've already signed a contract with Amazon. You need to use all of these Amazon services. So we were now in a situation where there was a design that had been prepared that was telling us we have to use all of these Amazon things, and we kind of had to start under-delivering in a way because we had to fit all of these things that the business had already committed to into our design. In the end, we spent a year or so building something that was incredibly complicated, again, for no particular reason, in my opinion. And the system actually never really got shipped. So I left before this ever launched. And just before this talk, I actually got curious. I went to their website. It looks like they launched the very first version, and it does approximately what our prototype did, like 7 years ago or more. All right. After we under-deliver, we move on to firefighting. So this is when our code kind of meets reality for the first time. So what ends up happening is that you first ship your devices, you turn on your web service or whatever, and it doesn't work. The smartwatch crashes, it doesn't show the time and the location of the user. Your web service just shows some kind of server error, and you start for the first time discovering the real problems that your under-delivered solution actually has. This is often called firefighting by SRE-type people or operations people. And it's because you kind of can imagine that you end up in a situation like this girl in the picture, where everything around you is on fire and you're trying to stay focused and just keep the thing running. The other stages that I talked about, over-engineering, under-delivering, they can be mostly overcome. Firefighting is something you will never completely get around. I'm pretty sure of this. So there's always, even if you have the best design, the best implementation, there's going to be something unexpected that happens in production when your thing gets in the hand of real users. So firefighting, again, consists kind of 3 different things. There's feature issues, which is business logic not working as expected. It's bugs in your system, all these kinds of problems. This is something where you may just not have considered a concrete edge case or something, and you need to go back and fix the bugs. The second one is stability issues. For example, maybe you misconfigured your database and it doesn't actually handle more than 5 users or so at the same time. And you will need to deal with these problems. You will have operations people that are getting phone calls at night to fix your system that isn't really working. And you end up getting stuck in this sort of paralysis state. So instead of developing your system further, adding more features, making it do more of what the business, for example, wants it to do, you end up spending all of your time kind of on firefighting, on dealing with these other 2 problems, and your system isn't really moving forward anymore. And this is a really bad state to be in, because the business at the same time will want you to add more stuff, and you may end up in a situation where things actually get worse, because firefighting, well, it's some people spending time on that stuff the business is willing to pay, but this scales badly in the long run. My example for firefighting is actually a legendary, very well-known project. It's not something I was personally involved in, but I picked this because if you find this interesting, there's a lot of stuff you can find about this particular failure that you can read on later. So in 2013 or 2012, approximately there, the US government tried to make a website. It was called healthcare.gov, and the idea was that people could go onto that website, compare the prices and so on of different insurance plans and buy an insurance plan. This project had a budget of something like $100 million, which they used to write this web service. And they split this money up along a large set of companies, different contractors and so on. They were trying to build kind of a working system there. What actually ended up happening is that when they turned the system on for the first time, 6 people managed to buy insurance, and then the thing completely crashed and it wasn't working at all anymore. And it took them over 3 months and a specifically hired technical search team, as they called it, with engineers from various large tech companies such as Google to try and get this thing into an actual working state. And the problem that they were running into was obviously everything that I've said before. There was no clear design. There was no clear understanding of the complexity involved. They didn't really integrate well with all the insurance companies and all of this kind of stuff. And this was a huge embarrassment at the time for the government there. And that's why it kind of turned into this legendary thing that you can read more about if you want. In terms of numbers, one thing I found interesting is that fixing this after the initial launch, the 100 million had already been spent to implement the system. And fixing it cost over 900 million in addition. So the system ended up costing over $1 billion just because of under-delivering, over-engineering, and so on. That is 10 times more than they had planned for. And the final stage that you get to is kind of the legacy situation. So this image is actually from an internal series of comics at Google that were kind of making fun of the corporate culture of the company internally. And the guy that makes these comics, he left the company and published them also. So you can actually go and find them on the internet. They're called Gumics. At Google, this is kind of a classic scenario. You want to do something, you have some kind of problem that you need to solve, and you try and figure out what is our current solution to this problem. And it turns out there is like a ready-made solution, but people will tell you, this thing is deprecated, don't use this, this is a legacy system, like don't even think about it, it's not supported and so on. And you're like, okay, so what am I supposed to do? And they're like, oh, well, we have this new thing, but it's not really done yet. It doesn't really work, it doesn't have all of the features, and you're like, well, what am I supposed to do? And this is a classic kind of legacy situation that things end up in. So a system, for some reason or another, ends up being deprecated, no longer maintained, and it kind of just withers and ultimately, maybe if you're lucky, dies in the end. While a new thing comes along, shiny new thing, and gets all of the resources and attention. Again, as with the other things, kind of 3 main points. So the first one is that you lose knowledge over time. Remember what I said about the definition of a large system? The fact that you have multiple generations of developers working on a thing. There might be people who wrote the thing initially, they're no longer around, they probably didn't write documentation, and the information that was in their heads just kind of goes away. And you end up in this kind of situation, which is a literal thing that's been said to me at work at some point, which is nobody knows how this works, but 40% of the revenue of our company is generated by it. So all that remains is some sort of knowledge about how to keep it running, but nobody can really make any changes anymore. You also get unpaid technical debt. Technical debt is the idea that you take shortcuts when implementing a system, and each of those shortcuts really is something you should fix somewhere along the day, somewhere along the timeline of the project. So in some sense, you take a loan by making a shortcut, and you really should be paying back this thing at some point, refactor it, rewrite the code, improve the way you did that. But usually people don't, because there's some other more important thing to do. And when you end up in a situation with unpaid technical debt, it's very difficult to make changes to the system and operate it. For example, inside of the company, there might be some new hot technology that everybody has moved on to, some new framework, for example, and all of the mandates, technical changes, and so on that pertain this new framework no longer really apply to your legacy service. You end up living with sort of 2 different islands of things. This also very quickly turns into an integration nightmare. So for example, you might have a legacy system that uses some kind of HTTP-based API, and then further on, new systems in the company are all going to use, I don't know, gRPC or some other kind of protocol that is no longer what the legacy system was doing. And suddenly integrating with it becomes very complicated. You have to write proxy services that translate old formats into new ones and so on, and you build kind of this surrounding infrastructure around your legacy system that's just trying to keep it alive. This is not a great situation to be in, honestly, but it happens all of the time, and I think anyone you talk to with some experience from large companies has some stories like this to tell. I actually have an example, which is from Yandex Taxi specifically. So originally, when Yandex Taxi was written, I think it's 13, 14 years old, something like that now. Originally, people wrote everything in Python as sort of a quick prototype thing in a single monolithic service. And that service kind of did everything related to ordering taxis. That is, selecting drivers, checking where people are, tracking the location of cars, all of this in kind of one service. And that thing did not scale. It was written in kind of prototyping style Python. It ran into technical limitations very quickly, and people had trouble just keeping this thing operationally alive. There were technical issues all of the time. At some point, a decision was made to rewrite everything in C++. I don't want to comment on how well of a choice C++ is in this case, honestly. But at least in terms of performance and so on, it makes sense to move to something that is sort of more fitted to the scale that you're trying to operate at. So what they did is they wrote a thing called backend CPP. That's because the old system was called backend Pi. And it was sort of a backend framework for C++ in which they could also, in a sort of monolithic service, integrate all of these features. And over time, a lot of the features of the Python system were ported over to C++. This happened fairly quickly. And we ended up with a sort of monolithic C++ service which replaced the previous monolithic Python service. But then something interesting happened. Some people came along and were like, what if, instead of having this monolithic thing, we actually start building microservices? So microservices give you the ability to structure the way that you do your development slightly differently. You can align your team structures more with the business. And people wrote this thing called userver. Userver is actually an open source project. You can go and check this out at userver.tech. It's the thing we use for basically all of the backend services that are written in C++ at this point. So userver was much more modern than backend CPP in various ways. It had like out-of-the-box support for like metrics, monitoring, logging. It had a great async I/O engine for like performantly implementing HTTP servers. And people kind of started moving over to userver. But the thing is, we have things of very varying complexity. Remember I said earlier there's a service that tells you something like the color of a car. That's very simple to rewrite in userver. But doing something like the matching of specific drivers to people is much more difficult. So this stuff actually remained in backend CPP. And we ended up in a situation where we had an old solution to the problem and a new solution to the problem. It's exactly the slide I was showing you earlier, where like backend CPP deprecated, please don't add any code here. Userver, well, not everything is kind of ready yet. We're still catching up with some parts. And you're like, what am I supposed to do? And we actually lived with both of these systems for 6 years, which is quite a long time in terms of tech companies. So backend CPP kind of kept living on a life of its own and had some people maintaining it. And our technical leadership at the time was thinking that we're not going to be able to like do a big migration project and get rid of this. But actually, this migration project was launched last year, and it was done successfully by one of my colleagues, Lyosha. Lyosha, to do this, he kind of built a bunch of automated tooling. This is a slide from a talk that he gave about this thing. I just liked the slide so much. I stole it from him. Sorry, Lyosha. Where essentially he wrote some Python scripts that used sed and arc. Arc is our version control system, and a bunch of if-devs inside of C++ code to kind of create a semi-automated migration from backend CPP to use services. The idea here was that we can adapt the APIs, we can keep the existing C++ code in backend CPP very similar to how it would be in the future, and just kind of like change things out under the hood. And ultimately, after doing this, Lyosha ended up deleting in a single commit over 2 million lines of code. It's sort of a legendary commit. This was when backend CPP was fully migrated into use services, so we kind of finally got rid of the legacy. However, I want to be clear about one thing. This is sort of an exceptional success story. Usually legacy systems do not get migrated from. They just live on forever. If you look at some of the large banks that exist that have been around for a while, there might still be services running on IBM mainframes written in COBOL from the 80s. And this is kind of a classic situation that many large companies end up in. All right, let's summarize the stuff that I said so far. So what happens at the beginning of a project is that instead of making a clear, understandable, well-thought-out design, we end up over-engineering the project, dragging in additional complexity, doing stuff that kind of doesn't really help us solve the real problem we have. After that, we go on to implementation, but instead of just neatly writing the code that we're dealing with, we end up under-delivering. We find more complexity along the way, things don't really work out the same way we planned, and it turns out that we kind of get this horse drawing, ultimately, that isn't really like the vision that we had at the beginning. And then we move into production, but instead of a smooth launch, we get technical issues. So we are dealing all of our time firefighting, we are paralyzed, we can't add new features, we can't really do anything more with our system. This is a bad state to be in. And ultimately, maybe somebody comes along and says, okay, let's just delete this thing, we'll write a new system, the new system is going to be great, it's going to be much better, but the migration ultimately never happens, and all of the stuff just lives along. Does that make sense so far? It's important that we're in sync here. All right, seems like a good sign. So what I actually want to propose, we're moving on to how we can prevent this kind of thing from happening. What I want to propose is that we extend this life cycle that I've shown with one more thing, one more state that we call maturity. My idea here is this: we can never really avoid all of these things. We will always have some degree of over-engineering or under-specifying our design or whatever. There'll always be problems during implementation, and we'll always have some sort of initial state after launch where we're dealing with issues that we didn't anticipate. But if we do all of this right, instead of continuously living with firefighting and ultimately deprecating, maybe the system can mature and kind of end up in a stable state. So we can end up in a situation where there's one component in our system that's sort of older in relation to the others. It's not using the same kind of technology, but it works very well. It's very well understood, and the behavior of it is basically what we want. There's actually lots of examples of this being done successfully. Who has used email, actual email, ever? Very few people, I'm surprised. I guess I'm old at this point. Email is actually a protocol from the 1970s, and it still works completely fine. It went through some iterations at the beginning. Some things were improved a lot over the years, but the protocol, the implementations, and so on, they're pretty rock solid. There's really no reason to replace them with something else at this point. This is a state that I call maturity. So there's three things that kind of lead up to this. There's issues actually getting fixed. So over the time that we spend firefighting, we figure out what bugs we have, what technical issues we have, and we start kind of putting everything together in the correct way. You could say that the system sort of anneals into a working state. Annealing is something from metalworking, from material science, where imagine you bend like a paperclip or something, it eventually breaks, right? If you wanted to restore the metal to its original state, what you would do is heat it up repeatedly and then slowly and controlledly cool it down. You can look at firefighting as doing something similar. You're kind of constantly on fire, and you're heating up parts of the code bases by making slight changes that fix the immediate problems you're dealing with. And ultimately, your system anneals into a much more stable, much more comfortable position. The other thing that happens during firefighting is knowledge is built up. So your operations engineers, your developers, and so on actually understand what the code they wrote does, and they actually understand how to operate it, what kind of behaviors it exhibits in production. And the third thing is that there's always some kind of improvements that can still be made to the system if your fundamental architecture allows it. So as you do the first two things, you notice that there's actually some small but very significant changes we can make in our implementation of this thing, and it will make everything much better. The example I have here is something from Google. Who's watched Star Trek? This is going to be another one of those questions where I'm just old, I think. Literally nobody has watched Star Trek. Okay, go and watch Star Trek. It's old, but it's great. So in Star Trek, there's something called the Borg, which is sort of this alien race. If nobody knows about Star Trek, I'm just going to skip this part of the explanation. And Google has a system that's also called Borg. This is its logo. Borg is Google's scheduler. So for all of the data centers, for the millions of servers that Google runs, there's this one single central thing called Borg, which orchestrates which things are run where. It solves various problems for them, such as, for example, let's say you have a data center in Australia, people are asleep at night in Australia, you're still paying for the electricity and so on. Borg helps them utilize those resources for things that are sort of not as time critical. So you can kind of offload computation to points where you have resources available. They wrote this thing, I don't know, over 20 years ago, I think. 2004, somewhere around that time, plus minus 2 years, I think. The paper that they published about this in 2010, I think, mentions that the initial design was kind of drafted up in 2003 already. So this is a fairly old system. I think, who was born in 2004 or later? So there's people in this room that are younger than this system that is running Google. The thing that happened with Borg is that they implemented this first version of sort of Google-wide scheduling of everything, of all of their resources, all of their CPUs, all of their storage distribution, their video cards, whatever else they have. And this was Borg. After some years of operation, the company got extremely large, and they started running into sort of scaling issues with Borg. For example, it had central components that would have to take a lock on a whole data center and kind of block and slow down operations inside of a single physical data center. And some really smart people at Google sat down and they were like, okay, we're going to do the classic thing. Borg doesn't work. We're going to write a new thing. And it's going to be called Omega. It's going to be great. The upgraded Borg. So they implemented Omega. They wrote a new scheduler. They fixed all of these kind of hotspots problems and so on that Borg had. And they ran some tests, and it turns out it actually worked really well. But then they talked to the SREs, and the SREs were like, you want us to migrate something like 2 or 3 million servers from one system to another while running all of our production services and so on. Are you crazy? And what the SREs pushed for was actually taking some of these improvements from Omega and integrating them into Borg. So the twist here is that Omega never actually replaced Borg. Google never ended up in the situation where there's sort of this legacy system Borg and Omega the hot new thing. Instead, they took the architectural improvements. They already understood Borg pretty well and put all of this stuff into Borg and then moved on. So at the time when I left Google, which was 2020 approximately, Borg was still running everything, and I don't think that has changed since then. So this is a success story of what can happen if your firefighting goes in the right direction and your initial design is good enough to kind of allow you to make changes later. So what I'm proposing is that instead of trying to completely avoid over-engineering, under-delivering, and so on, we try and minimize the time that we need to get to this maturity stage. So if we look at our software lifecycle, we can accept to some degree that we're going to be stuck in these kind of orange-red first phases. But at some point, if we do everything well, we'll get to maturity. And we want to do that as quickly as possible. So what can we actually do about this? There's a couple of different things, but the really most important takeaway, and I'm going to repeat this at the end, is that you should try and catch the problems you have as early as possible. The idea here is that the later on in the life cycle of a system you catch a problem, the more expensive that problem becomes to fix. That is, if you catch a problem during design, amazing. You just fix it. There's nothing else yet. If you catch a problem during implementation, okay, you have to rewrite that code. It's slightly more expensive than fixing your design, but it's still doable. If you catch the problem in production, well, now you have to quickly fix it, roll out an update, make sure everything works with the old and the new version, and so on. It becomes significantly harder to fix problems the further along the timeline you go. So how can we do that? One of the most important things about this, I think, is not getting stuck in the metaphorical tar pit. Remember, I had a slide at the beginning where I mentioned that there's something called accidental complexity in software systems. So accidental complexity is an idea introduced in a couple of different papers. One of them is called Out of the Tar Pit. It's something I really recommend reading if you're into this kind of thing. And the idea goes kind of like this. Imagine you're writing a web service for ordering flowers. I don't know why I'm using this example all the time, but I think it's understandable for most people. So when you're dealing with a flower ordering service, there's some problems that are kind of directly flower problems, you could say. So you need some kind of logic, for example, having users select the color of flowers or the size of flowers. And you might have to deal with some of the stuff related to delivery, like scheduling your drivers or whatever. And these are kind of all inherent problems related to flower delivery. But at the same time, when you're writing the system, you end up doing a whole bunch of other stuff. So you have to pick programming languages. You have to pick frameworks that you use. You have to write build instructions. You have to figure out how to deploy your system. You have to set up monitoring for your system. You have to do all of this kind of other stuff that is not a flower problem, if you will. And there's this idea that this kind of stuff is called accidental complexity. It's not complexity inherent to your problem. And you want to minimize that, because if you have too much accidental complexity, you end up in a situation where like this guy, you are stuck in the tar pit and you kind of can't get out of there. You can't do the things that you actually wanted to do. So during design, and this is really the most important thing, you should try and minimize the complexity of what you're trying to do. And you should try and get rid of all of these accidental problems that really aren't necessary. So in order to do this, you need to understand a bunch of design trade-offs. So when designing, you can spend infinite amounts of time designing something ahead of time. And whether or not this is worth doing kind of depends on what kind of system you're writing. And you need to understand what things you're trading off for one another when you're spending time on designing versus implementation. So for example, designing in advance means it'll take longer until the point when you actually start prototyping, when you have some kind of thing that you can show to people, some kind of real implementation code. But on the other hand, it means that you end up having less technical debt. There's more things that you thought about in advance that you caught during design, and you're kind of spending the time to the point where you start being able to implement to the time that you will need later on to keep your system stable and maintained. The second thing is implementation quality. If during implementation you spend more time on complicated test infrastructure that helps you really figure out whether the thing is working before you ship it to users, you might end up having a slightly slower delivery cycle. It will take you more time to implement this. But ultimately you end up with easier maintenance, and your software system hopefully ends up having fewer bugs than it otherwise would. And the other thing is coordination with other teams. This doesn't really apply if we're talking about like a small hobby project that you're writing, but it does apply in the case of, for example, working at a big company like Yandex. If you're doing everything on your own, you can move very fast. You don't tell anybody what you're doing. You're like, I'm going to solve this problem, just give me a weekend, and then you show up on Monday and you have this kind of complex thing that you built over the weekend, but nobody other than you knows how it works. And you trade this off against sort of coherent systems design, where before going ahead and doing that, you make sure everybody understands what you're trying to do, critique that told you things where you might be overlapping with other initiatives in the company. And you again trade off this time. You can do everything quickly on your own, or you can spend more time synchronizing with everybody else and get a slightly more coherent sort of system design. Whether or not these things are worth doing really depends on what you're doing. So there's an important question you need to ask yourself, which is how long is your system going to live? For example, if your system is something temporary that just needs to like run a temporary migration project for a year or whatever, you can spend slightly less time on design because you have more of an allowance for doing it in a way that is going to be qualitatively worse. Another example of this, actually not directly related to time, is what I said earlier about rockets. So if you're launching a rocket, you probably want to spend as much time as possible before the design, because that code in some sense is eternal. It lives forever. You only get one try. You cannot ship a software upgrade to a rocket that's being launched. So think about kind of what kind of life cycle are you dealing with, and what kind of evolution are you expecting from your system? Another important thing is, why are you building the system at all? So this is important. Actually, it sounds kind of stupid when you write it down like this, but the point is there really a reason why you're building the system, or is this the first thing that your mind jumped to when you heard about the problem? There's a guy called Rich Hickey. He wrote a programming language called Clojure. Maybe some of you have heard about this. And he gave a famous talk called hammock-driven development. A hammock, I don't know, you probably know, it's one of those things that you can hang between trees and kind of lie and chill in the forest, for example. And the idea with hammock-driven development is somebody comes to you and is like, we need to fix this problem. And your first idea is, wow, I have to write like a service that does this immediately. But he says, take a step back, go chill in your hammock for a few hours. Don't write any code, don't write any design. Just let your brain work on the problem. And you might figure out that actually you don't need to write a new service. There might be some much simpler solution to the problem. So the why is really important to understand. You should be sure that you're building the system for something that's like a coherent reason. The next thing is, what is the scope of the system? So remember I was talking earlier about how you might be building this flower delivery service, but instead of focusing on the parts of the delivery specific to flowers, you start building like a generic delivery service for furniture or whatever else. This is scope creep. It means that you didn't clearly understand what your system needs to do, and you start expanding out into more generic things that are not really related to the stuff that your system should be doing. So it's important to sit down at the beginning, figure out what is the scope and what is not in scope. Explicitly say, okay, we could be doing this other cool thing, but it's going to slow us down, it's going to be complicated and so on. Let's not do it. It's not absolutely necessary. So figure out the scope of your systems. The next thing is, what are your constraints? Your constraints is a lot of different stuff. For example, if you know C++ and you don't know, say, Rust, it's probably not a good idea to write an important new system in Rust, because you're going to spend time learning Rust, and so it might be a cool thing to do, but still you already know C++, and you're going to spend some of your sort of potential energy that could go into making the system better on learning a different language. Another thing is, how many resources do you have available? How many people are available to work on the thing? You kind of need to account for all of this. It's very easy to make a super complicated design that you'll never be able to implement simply because you don't have enough time. So this is something that always needs to be kept in mind. And finally, Once you've understood all of these things, why are you building the system? What is the scope of your system? What are the constraints under which you're building the system? You should do the smallest possible thing that matches all of these constraints. So you should be, in a way, lazy, I would say. Laziness is a good quality for a developer. You should be lazy and figure out the smallest thing you can do, the least effort that will solve your problem, because that's most likely to be the simplest and most sort of logical thing that you can maintain along the road. The next thing is that you should attempt to catch problems as early as possible. I already said this, I just wanted to write it down one more time, very explicitly. Whenever you move on to the next stage, you go from design to development and so on, make sure that everything that really could be an obvious problem is already caught. In implementation, if it's like a long-lived system that you're building, make sure that you cover the most important things with tests so that you figure out what problems you have before you move on. And finally, make sure to keep your napkins. What I mean by this is all of the stuff you wrote down, all of your little notes, your designs and so on that you made at the beginning, keep them around. They're very important information for people that are going to deal with your systems in the future. I have an interesting example of this actually. Back when I worked in Yandex ads, my team moved from one room in our office to another. And my team had previously been in that room for like 7 or 8 years. And the desk I sat on had like a little drawer under the desk, which I never looked at. It was just there when I moved in. And when we moved out, they told us we have to get all of the furniture out of the room. So I was like, okay, let's open this drawer, figure out what's in there. I opened this drawer and it basically looked like this. And it turns out that this was the seat where Valery Stromov earlier sat. He's the CEO of Alisa now. But he was actually a developer on our backend services at some point, very early on. So the notes that we found in his desk actually had a lot of very important information, which wasn't really formalized anywhere else. And having these notes available earlier would probably have helped Yandex along the way quite a bit. So always make sure that all of the information you write down, everything that's in your head, dump it somewhere, keep it around for the people that come after you to sort of ensure a smooth handover. And if you do all of these things, I think you have a good chance of making systems that are going to be just a little bit better, just a little bit more stable, just a little bit more long-lived, and just a little bit less annoying for the site reliability engineers. Thanks a lot.